This is Lecture 9B for Calculus 2 on the direction fields associated with differential equations. As you might recall from the first lecture on the introduction to differential equations, the solution of a differential equation is a functional form. These solutions can be very difficult to obtain. However, we can find graphical information about the solution directly from the differential equation itself. There are two important pieces of graphical information. One is the direction field, and the other are lines of equilibrium and the behavior of solutions near the lines of equilibrium. First, we'll discuss the direction or the slope field, or sometimes it's called a vector field, associated with the differential equation. Right. This is a graph, and the graph consists of small, equal length line segments that are tangent to the solution. The values of these line segments are calculated from the differential equation. The solution of the differential equation snakes through this direction field. You might have looked at these direction fields in calculus, the first semester of calculus. But I'll give you here some examples. By the way, direction fields are very complicated, or it's very involved trying to calculate the direction fields. It's more important to just appreciate them. Here are two computer-generated direction fields. This is for the function. Write it down here. It's kind of small right there. It's the first derivative. dy by dx is y plus x. Okay, just for practice, what kind of differential equation is this? Well, there's only one independent variable, and that's x. So that makes it an ordinary differential equation because there's one independent variable. There it is right there. Okay. The highest derivative is the first derivative, dy by dx. So it's first order because the highest derivative is the first derivative. So it's first order. All right. Okay, is it linear? The derivatives and the function are raised to the first power only. So this is a linear equation. All right. Is it autonomous? If it's autonomous, then the independent variable does not appear explicitly. Here the independent variable, which is x, appears explicitly, so it is not autonomous. And it is non-homogeneous. To be homogeneous, every term has to include either the function or its derivative, but we have this x by itself, so it is a non-homogeneous equation. Right. But how this direction field was obtained is by evaluating this first derivative. Remember, the first derivative gives the slope of the line tangent to the solution, so the value of that determines these particular slopes. Okay. So when x is 0 and y is 0, dy by dx is 0, and right here the direction would have no slope, zero slope. Okay. Okay, if x and y are positive, then dy by dx is also positive, and you see these little vectors are going up. That's a slope. Here, where x and y, the combination is negative, then they slope down. That would be the case right through here. Okay, or over in here. Now, after you've created all these little vector fields, then you can snake the solution curve through them because the solution has to be tangent to these curves, to these vectors. So if you start the solution here, you see how it snakes through. If you started the solution here, you can see how it has to snake through this direction field. Here's another. Dy by dx equals the sine of x plus y. Okay, what kind of differential equation is this? It's an ordinary differential equation because it has one independent variable, and that variable is x. All right. What is its order? The highest derivative is here. It's the first derivative, so it's first order. Is it linear? No, it's nonlinear. dy by dx is raised to the first power, but the function itself appears as the argument of the sine function. This is highly nonlinear. Is it autonomous? No, because x appears explicitly here, so it's not autonomous. Whoops, I'm out of room. And it's non-homogeneous as well. Okay, so by taking values of x and y from the plane, this is the y-axis, here's the x-axis, adding them up and evaluating them as the argument of sine, the sine function, you get the value of the first derivative. This is the slope of the solution as it goes to the point xy. So at each point xy, all right, then you can find the slope right here. Those are those little line segments. Those are little tiny slopes tangent to the solution. Then depending on where the solution starts here, well, they've given some points here. Then you can see how it snakes through the field, direction field. Another way, perhaps more, that makes more sense to some of us, is that this direction field is the current in the river. Now, if you put the stick in the river right here, you can see how it will follow the current. That's all. Let's look at another example. In this case, the derivative, well, actually the function itself, not the derivative, is given here. It's kind of hard to read, but we're just using this for illustration purposes. Here they put arrows on the little lines that make up the direction field. It makes it a little easier to read. So you can see that if this is the current in the river and you put your stick in here, I'm sorry, get the pin here. So you put the stick in the river here, what will it do? The current will take it and it will flow like this. If you put the stick in the river here, it snakes through the direction field like that. Alright? So again, these are hard to draw. It's more important at this point to just appreciate the direction field and understand what they mean. The little tiny lines are slopes, actually the derivative of the solution vector, or the slope of the tangent line of the solution at that particular point xy in the plane. The solution curve snakes through the direction field, obeying the slope.